Hello, I welcome you all in this course on mechanical measurement systems, and today we will continue to discuss first order system. Now in today's lecture, we will discuss the step response of first order system. And we will take a few examples also to have a clear insight of how the system behaves first or for the step input. So first of all, let us start with the step input to the system. So when there is a step input to the system, on x-axis it is time, on y-axis it is qi, input quantity. So when there is step input to the system, the input characteristic curve is something like this. At time is equal to 0, the input has increased from 0 to certain value. For example, in a voltmeter, when voltmeter is connected to a main line, right, and just when the moment you connect it, right, the input is 220 volt. Whatever the voltage is there in the main line, the input voltage is 220 volt, right? It is the voltage which is in the main line, but the voltmeter, this analog voltmeter, takes some time to display that value. And this is how we judge the response of the system, whether it moves very fast or the needle moves in a very sluggish manner. Another example of step input can be given with the mechanical point of view is like quenching of rods or putting thermometer in a boiling water. So if the temperature of the thermometer is at atmospheric temperature 25 degrees centigrade, and in a pan there is boiling water. So the moment the thermometer is dipped in the boiling water, water is boiling at, let us say, 99 degrees centigrade or 98 degrees centigrade. So the moment the thermometer is put into the vessel, there is a step input to the thermometer, and step input of temperature is 98 minus 25. It is going to be 73 degrees centigrade. So mathematically we can say there is a 73 degrees centigrade step input to the thermometer. And input curve can be shown like this. Now response of thermometer. Now response of the thermometer or the voltmeter, in ideal case it has to be like this. It should follow the input curve. But due to the inertia of the instrument and due to many other reasons, the output of the instrument for the first order instrument goes like this. And after certain period, it becomes very close to the input. And if you look at the error in the measurement point of view, in this region the error is high, and slowly the error is reducing and a steady state error is, at whatever the error is in the instrument, that will remain. But this error is diminishing with time. This is dynamic error, because error is dependent upon the temperature, the time. So this is a dynamic error and it is diminishing. Now we will do analysis, some mathematical analysis of this type of system. So for the purpose of mathematical analysis, first of all we will start with input qi. Input or output both are 0 at t is equal to 0. So when t is equal to 0, initially input and output both are equal and both are 0. So we are somewhere here. Now with time, input has increased to QIS. But output is not increased to QIS. Output will start increasing, and after certain time interval, it will become close to the input. So because this is a first order system, so for first order system, because this case is t is greater than or equal to 0. Now, if you remember the first order equation, the first order equation is lambda d plus 1 QO is equal to KQI. This is the first order equation, generalized equation. Now, here K is sensitivity, because when we are measuring, for example, temperature with thermometer, input is in degree centigrade, output is in millimeter, displacement of mercury column in the thermometer, and that is in millimeter, displacement of mercury column in the thermometer, that is in millimeter. So, in that case, the sensitivity is, the dimension of the sensitivity will be millimeter per degree centigrade, mm per degree centigrade. So, K has to be taken into account because we have to match the dimensions also. Now, here if we try to find solution for this, with the help of initial conditions, so at t is equal to 0, so first of all, we will take complementary function. So, complementary function is going to be equal to lambda d. So, in order to find complementary function, we will take lambda d plus 1 is equal to 0, and it has one root, and the root is minus 1 by lambda. For complementary function, we will solve this equation and we will try to find the roots for d, and because the order of the d is 1 and the roots is minus 1 by lambda, and the solution for this complementary function will be c e raised to power minus t by lambda. If you remember in my earlier lecture, then you can easily conclude that complementary function is going to be like this. Now, particular integral. Particular integral is going to be equal to KQIS. This is input quantity, QIS, input quantity QIS, right? Now, we will add these two and we will find the solution as QO is equal to QO complementary function plus QO particular integral, and this will give the solution of equation as QO is equal to C e raised to power minus t by lambda plus KQIS. KQIS. Fine. Now, here we will put the initial condition. Initial condition is QO is equal to 0 when QI is equal to 0 at t is equal to 0. So, this is 0, right? And then KQIS. So, this is 0 is equal to C e raised to power minus t by lambda plus KQIS. Now, here in this case, because at t is equal to 0, so this term will also become 1. So, C is equal to minus KQIS, right? And when we manipulate this C in this equation, we will get the finalized form of the equation as QO is equal to KQIS 1 minus e raised to power minus t by lambda. okay, because from here we have derived the value of C, and by putting the value of C in this equation, because in this equation there is only one known. So one boundary condition is sufficient. So in order to find this constant, we have just manipulated the values from initial conditions, and this is the final equation. Now from this equation you can easily judge that for large value of t, this expression is going to be, this value is going to be 0 or tending to 0. When t is tending to infinity, this value is tending to 0, and then Qo is equal to KQIS. Okay. Now because for certain value of t can be less than lambda also. In that case, some error will be there in the measurement, because lambda is 5 seconds and we make measurement after 2 seconds. T is 2 seconds. So definitely we will find that there is a significant error in the measurement. So in order to find error in the measurement, EM for the dynamic response is QI minus QO upon K. That is input minus input we are getting from here, QO by K. And this will lead to, here in this case, as QIS minus, from here it is QIS 1 minus e raised to power minus t by lambda, and it is going to be equal to QIS e raised to power minus t by lambda. This is error in the measurement, and definitely it is divided by K and Q by K. Okay, it is already divided, so we will not do this. Right? Or we can say that error in the measurement divided by input is equal to e raised to power minus t by lambda. In many ways it can be written. So this is a non-dimensional form. This one we can say a non-dimensional form of the error in measurement, e raised to power minus t by lambda. Now after this, so response of the system, as we can see here, response of the system is faster when the value of lambda is small. When the value of lambda is small, the system will respond quickly, right? And there is a settling time for the instrument. Settling time means when input is given, the output starts changing, right? And after certain time interval, it gets settled in the tolerance limit of the measurement. That you can say the measurement is in the range of 5% or 2% of the measurement. So that is the settling time. And in first order system, there is never overshoot. You must have observed in some of the instrument when input is given. Suppose in a voltmeter, you must have observed in this some voltmeter also, when input is given. This happens especially in the electrical instruments, right? And then the input is 200 volts, but it will overshoot. And then after certain oscillations, it will come restore to the steady state. This happens in some of the weighing machines also, where springs are used. The needle will, when you put the weight on the weighing machine, that is also a sort of step input, right? You are just putting 1 kg of the object to the weighing machine, then needle will start oscillating. So that is not, this kind of response is not the first order system response. In first order system, when you put the weigh on the weighing machine, the needle will move and it will attain the value within the tolerance limit of the measurement. And this is known as settling time. So in first order system, if the weighing machine is of the first order system, if weighing machine is a second order system, then oscillations will take place. So, for a quick response of any system, first order system, the lambda has to be low. The value of lambda has to be low. And now let us recall our previous derivation for the thermometer, where we calculate the value of lambda as rho C VB divided by UAB. Right? Now, rho is specific heat of the bulb, fluid which is filled in the bulb. Sorry, rho is the density. Rho is the density of the fluid which is filled in the bulb. There is a bulb in the thermometer. So, whatever fluid is filled in this bulb, the density of that fluid is rho. C is the specific heat. So, rho and C has to be high because these are physical properties of the fluid. So, we cannot control them. They are physical properties of the fluid, whether you are using mercury or some other fluid. But in any case, the product of rho and C has to be high, as high as possible. Right? And then there is a term VB, volume of the bulb. Sorry, for lambda it has to be as low as possible. Sorry, I'm sorry, it is not as high as possible. Rho C has to be as low as possible. As high as possible, it will increase the lambda. So, in order to have low value of time constant, this rho C has to be as low as possible. Okay? And then VB, volume of the bulb. This has to be as low as possible, U as high as possible, and AB as high as possible. Now, here there is a problem. The problem is when we talk about this K for thermometer, right, sensitivity, then it is about EX, VB and AC. This is sensitivity of thermometer. I am talking about liquid in bulb type of thermometer. So, here in order to have high sensitivity, we should have high bulb volume, right? This is expansion coefficient, this is cross section area of the tube where the fluid is rising. So, now we have to strike a compromise. If you want to have low value of lambda, then VB should be low, volume of the bulb should be low. And if you want to have high sensitivity, then volume of the bulb should be high. So, a compromise has to be struck between these two. Now, area of the bulb, it should be as high as possible, and U, overall heat transfer coefficient. Now, this is important. We cannot control overall heat transfer coefficient, but we can always assess the overall heat transfer coefficient. Suppose the thermometer is measuring some high temperature fluid which is flowing in the pipe. In that case, U will be high. When thermometer is measuring the still air, for example, air in this room, then U will be low. So, it is possible that a thermometer we are using is, application is flow of, to measure the temperature of liquid metal in a pipe, liquid metal flowing in a pipe. U will be quite high, or flow of hot fluid or hot oil flowing in a pipe, U will be high, time constant will be low, and time constant, let us say, maybe around 3 seconds, for example. Another application of the same thermometer, I want to measure room temperature, this room temperature, and the air is not moving. Time constant may be 30 seconds, because time constant will depend upon U. So, there is no fixed time constant for this type of thermometer. So, when you purchase, or when anybody purchases a thermometer, and if you are interested to know the time constant, then you must ask the vendor, or you must ensure that for which application you are going to use this thermometer. Suppose it is specified 3 seconds, but you are using the air temperature, the time constant is 30 seconds. that will creep a lot of error in, that will result in the creeping of a lot of error in your measurements. Now, for a step input, if we have different values of lambda, right? Suppose the lambda is very low, the value of time constant is very low. Then lambda is very low means the response of the system will be like this. It will not overshoot, it will go like this. Not even like this, it will be like this. So suppose this is lambda 1 and this is lambda 2 and lambda 2 is greater than lambda 1. In this case, the response is sluggish. You have another instrument which has again lambda 3, this is lambda 3. So lambda 3 is greater than lambda 2 is greater than lambda 1. Right? So this is how the system responds for different time constants. Now, if we draw a curve for different values of time constant, first of all, let us say t is equal to lambda. When t is equal to lambda, in that case, Qo is equal to Qis 1 minus e raised to power 1 by 1 or t by t or lambda by lambda, or Qo is equal to Qis 1 minus e raised to power minus 1. Right? And when we can take, we just Qo is equal to KQis. Sensitivity also we have taken into account. Now, if we take Qo by KQis, Qo by KQis, it is going to be 1 minus e raised to power minus 1. So, if we take this value, it is a constant. It is 0.632, right? So we can say that when a step input is given to the system, we can define the time constant now. When the step input is given to the system, it is the time required by the system to attain 63.2% of step input. Not 62, this is a common mistake, not 63.2% of final value, because now we have started here in this case we have started step input from 0, that is final value minus initial value. I will solve one numerical, then it will give you the clear insight. So we can say that it is time required by the instrument to attain the 63.2% of step input. Now if instead of 1, suppose I take t is equal to 2 lambda, then I will be getting Qo by KQis is equal to 1 minus e raised to power minus 2, and this is going to be equal to 0.8865. Now we are closing, the time is increasing, we are closing to, we are going closer to the input. Now again we take t is equal to 3 lambda. When we take t is equal to 3 lambda, then we get Qo by KQis as 1 minus e raised to power minus 3. And this gives the value 0.95. Now we have reached the 95% band for 5% band of the final value. Again, we take t is equal to 4 lambda. When we take t is equal to 4 lambda, then Qo upon KQis becomes (0.982) within 2%. And for 5 lambda, we assume that we have attain the steady state. The steady state has been attained and the value has surely reached in the tolerance band of the measurement. So I have shown here in the screen, there are two figures. The red one is for different values of T and lambda, QO upon KQIS. As you can see, the value is increasing. The value is increasing for different value of time constant starting from 1, 2, 3, 4 and 5. Up at 5, you can see it is almost 1. Fine. Now, for the error in measurement. Now, error is measurement is, if you look at the error in measurement, error is measurement is error in measurement is e raised to power minus t by lambda. Dynamic error in the measurement. If you refer back, then error in measurement is e raised to power minus t by lambda. And here we have measured QO by K QIS, that is the response of the system, E1 minus e raised to power minus t by lambda. So when the response was here for t is equal to 1, if you remember, for step input, the response was 0.632. This is going to be 1 minus 0.632. So it is going to be 0.368. This error in the measurement. And finally, when lambda is equal to, so t is equal to 4 lambda, in that case, when this output input relationship was 0.982, the error in the measurement is going to be 0.018. So I have drawn both the curves for different value of t and t by lambda starting from 0, 1, 2, 3 and 4, and then output is, you can say it is rising, the output of the instrument is rising and it is attaining close to the input. Here I have written infinite, but if you go for the 5 lambda or 6 lambda, it is they are going to be equal. And error is measurement is also diminishing, and at the lambda is equal to 5, the error in the measurement is less than 0.08%, because at the lambda is equal to 4 t is equal to 4 lambda, it is 1.8%, right? So this is the characteristic curve for error in measurement and the output of the instrument. Now we can take one example. Now in this example, it is stated that a thermometer has time constant of 3 seconds. So time constant for thermometer is 3 seconds, right? So temperature, initial temperature of thermometer is 0 degree centigrade. It is dipped in the melting ice. So initial temperature is 0 degree centigrade. And there is water, hot water in a pan. In hot water in a pan, the temperature is 80 degree centigrade. This is T2. This is T1 and this is T2. When the thermometer is dipped in this hot water, the step input is going to be 80 minus 0 is equal to 80 degree centigrade. This is input, QIS input. If had it been 10 degree centigrade, step input would have been 70 degree centigrade. Had it been 20 degree centigrade, it would have been 60 degree centigrade. So input is 80 degree centigrade, time constant is 3 seconds. So what is the temperature which will be indicated by after 1.6 seconds? So this T is equal to 1.6 seconds. So T is less than time constant. When T is equal to time constant, it is only 63.2%. So it should be less than 63.2%. But mathematically, we will find here that output is theta. This is input. Theta, let us say theta I, input to the thermometer. 1 minus e raised to power minus 1.6 divided by 3. Now theta is 80 and 1 minus e raised to power minus 1.6 divided by 3. If we take this value of theta, then theta is going to be e raised to power minus 1.6 divided by 3 minus 1 minus this multiplied by 80. So it is going to be 33.1 degree centigrade. Initial temperature is 0, so we can always say the temperature indicated by thermometer is 33.1 degree centigrade. Now, for T is equal to lambda, this temperature would have been 63.2% of step in a, so it is less than 63.2% also, 33.1 degree centigrade. Now we can take another example also. Now in this example, the thermometer is suddenly subjected to input of 500 degree centigrade from 25 degree centigrade. So T1 is 25 degree centigrade, T2 is 500 degree centigrade. So theta I is equal to 500 minus 25, 475 degree centigrade. Right? Calculate the temperature indicated by thermometer after 1 second. So T is equal to 1 second. Time constant 2 seconds. Time constant is 2 seconds. Now here in this case, comfortably we can take theta is equal to theta I 1 minus e raised to power minus t by lambda. And now theta I is 475, 1 minus e raised to power minus 1 by 2. And when we solve this, we get the value of theta as 186.9 degrees centigrade. Now, in order to find temperature, this initial temperature will be added. So, add here initial temperature and then we will get the value of T1 sec or T3. We can get T3 as temperature after 1 second as 186 plus 25, 211.9 degrees centigrade. Right. So, simply we can predict the temperature after 1 second. Actual temperature is 500 degrees. We are far away from actual temperature. Because at 500 degree centigrade temperature, if it is steel, the color is, you can see the color. I mean, through color you can also judge. Because earlier days there was no thermometry or this temperature scanning of the surfaces, but the goldsmiths, they were very expert. Through the color of the object only they could identify that what is the temperature of the object. Though those estimates are not very accurate. I mean, the value may lie in a range of plus minus 25 or 50 degrees centigrade, but they could get fairly good idea about the order of temperature. This is all for today. So in the next class, we will discuss the ramp response of first order system.